Hi, in this video we're going to go through a sort of primer into the rational method. So we're not going to spend a lot of time trying to go through the concepts. We just want to do a brief overview and then we'll fill in the details in other examples. So what we're trying to do is figure out either given a certain event or with design values the way to size inlets and pipe structures for development. These are going to always be small developments. So the first thing we need to talk about is how rainfall works. So we need to understand about the intensity, duration, frequency relationship. So we can see that for a given duration storm, as you get to less and less likely events, the intensity is greater. So this is inches of water per hour. Also, we can see that as the duration of storm increases, the intensity decreases. And we know this to be true. It's intuitive. We think of things like it raining really hard for a short period of time, but that can't be sustained over a longer period of time. So choosing that right duration of storm is critical to making the correct design work. So we also need to talk about losses, and that is for an inch of water, how much is going to run off. So is it a half of an inch, is it a quarter of an inch? And for the rational method, we're going to use the runoff coefficient C. And C is basically the depth of runoff divided by the depth of precipitation, and so it's expressed as a ratio. So for example, for an asphalt roof with a 2-year design period, they're suggesting for every inch of water we would have 0.73 inches of runoff. And of course there's a lot of these different values of C. Basically this is a matrix of values of runoff coefficient that we could use. So for design, we need to keep in mind a couple of sort of base ground understanding of what's going on in particular in this figure. So for example, if we look at a cross section that's cut through this along this pipe, what we would see is the ground surface falling such that we could place a stormwater inlet right here and then another stormwater inlet farther down. So this might be 1.1, and then below grade, so that's the inlet. These are typically concrete precast box structures, so water is going to run to this inlet and this water is going to run to that inlet. So below ground we would have a box of concrete, and then a pipe that connects them together. So if this is 2.2, sorry, that's should be 2.1 right here. You can see that the black line it is the pipe that's draining 1.1 to 2.1, but there's also another pipe coming in laterally. So for 2.1 there would be another pipe coming in from the side. So that's the subsurface picture. So what we need to do is first discuss how to design the inlet structures. And essentially what that means is that for a certain amount of water that will be running to the site, how big does the inlet need to be? And that's going to be a function of the duration of the storm and the return period that we're designing for. So the return period is typically going to be defined by a municipality or local governing body. So the way it works, the equation for flow rate into an inlet is Q equals CIA. This is the area I is the intensity of the storm, and C is that runoff coefficient. So let's look at 1.1. So in this case, 1.1 is going to drain this entire area. And what we want to do is ensure that we are using the duration of storm that corresponds with the most runoff going into that inlet. And what it turns out to be the case in most situations is that we want to use the duration of storm that corresponds with the time of concentration and, for that area. So the time of concentration just describes how long it would take for water from the farthest part of the area to reach the inlet. How long does that? And the reason is, if we chose a duration that was less than that, then we may only actually have this area within the circle draining to our inlet. So the bigger area is going to produce more runoff, right? So we want to make sure that we're draining the entire area. If we used a duration storm that was longer than the time of concentration, then that would drain the entire area. The entire area would be contributing runoff, but the intensity of the storm would be less than the maximum intensity. So we know that as storms get longer and longer duration, their intensity is less. And so we want to use the greatest intensity that corresponds with our site. So to size the inlet, what we'll do is first figure out what the time of concentration needs to be for that inlet, and that will tell us what the intensity should be from this type of a figure. So we'll pull a value off of this and plug it in to this equation for intensity. We're going to get area off of a CAD drawing or something like that, and we're going to get the coefficient C based on land use, soil type, slope, and other design considerations, for example, return period being one. So that's actually a really easy calculation. Now we've got flow rate for what's going on into that inlet. From observation, we can see that whatever the flow rate is that's going in to this inlet, that's also the same flow rate that's going into this pipe. So those are the same flow rates, and we'll use both those same flow rates to size how big the inlet needs to be and also what the diameter of the pipe needs to be. So that's pretty straightforward, and we can do that same exact thing for all of these areas. So area 1.2 is right here. And so we would find out what is the time of concentration corresponding with the greatest distance of water travel. So maybe that is this dimension. And there's equations for calculating this. We'll go through it. It's just a function of slope and roughness and length. So now we've got our duration of storm for this, just for this inlet, and also for this pipe. That's great. 2.1 is a little bit trickier. So 2.1 is draining. So the inlet itself is draining this area. Okay, so we can use the time of concentration to get the intensity, and that's going to size the inlet for 2.1. Now, recognizing that the inlet is just draining the surface. Now, there's a pipe that connects 2.1 to 3.1. Now's where things start to get tricky, because what we need to do is we need to size that pipe such that we still keep in mind what the time of concentration is for the area the pipe drains. In this case, the area the pipe drains is this entire area. So we've got a new area. We're going to do an area weighted average for our C coefficient. And now we've got to figure out what our time of concentration is. So there's some possibilities for this. The first possibility is that this dimension time of concentration controls. That's one possibility. Another possibility would be that area 1.1, that has a drainage time, and it also has to have a travel time through this pipe. So we would compare these two travel times and use the one that's the longest, and that'll give us the duration of storm that corresponds with both of those areas being fully drained. There's one more possibility, and that's that area 1.2 plus its travel time through the pipe is the critical duration. So we're looking for the longest duration of these three possibilities, and we'll choose that, and that will be the intensity. That'll correspond with the intensity for sizing this pipe that connects 2.1 and 3.1. Then we subsequently march down through the rest of the design until we're finished. So the inlets are always only draining the area above the inlet, but the pipes are draining oftentimes multiple inlets. So we need to do multiple comparisons to figure that out. So we're going to go through all the details, and we're going to do some examples in class. I think that it's going to be pretty obvious, but this is going to give us a little bit of a head start and something that you can go back to review. It's relatively short duration compared to the class lectures. So we'll have more questions and answers and examples coming up. Thanks.